Okay, today's lab, we're doing lab number 11, earthquakes. And the purpose of this lab is basically to show how it is that scientists determine the epicenter of an earthquake. So an epicenter is basically where, if a fault moves underground, it generates an energy wave, a shock wave that then travels to the surface of the earth, and then it travels across the earth. And so that's called the epicenter. And the way we do epicenter location is we use 3 seismographs. So you have to have 3 seismographs, and you're going to draw circles with respect to the distance that those seismographs are from the earthquake, and how they determine the distance is by the arrival of the shock waves on the seismograph. So part 1 basically says use a ruler or a blank sheet of paper to mark and record the gap between the arrival of the primary waves and the secondary waves of the seismograph stations below in figure 1. So just to show you how this works, I'm going to scroll down here to this. So these are 3 seismographs. There's one seismograph at the very top, United States Geological Survey at Yuma, Arizona, one at the University of Nevada, Las Vegas, and one in San Jose. So you have to have a minimum of 3 seismographs. The more you have, the better. It means you're going to have more circles, but for this lab, we're going to keep it simple. And so notice that there are different waves. There's P waves, there's S waves, and there are R waves. We're not going to worry about the R waves so much. We're going to look at the P and the S waves. So if an earthquake occurred right where the seismograph was located, so let's say there's a seismograph at the University of San Diego, and that earthquake occurred right there, that was the epicenter. The P and the S waves would be together. They start together, and then as they move away from the epicenter, and they gain distance, and they move further and further away, these waves travel at different speeds. The S wave travels faster. And so what you see is a differential in the P and the S wave. So the wider the gap is, the greater the distance that that seismograph is from the earthquake. So just by looking at these 3, the P and the S waves for Yuma, for the University of Nevada, Las Vegas, and for San Jose State, you can tell that the USGS at Yuma is the seismograph that's closest to the epicenter of the earthquake, but it's not right at the epicenter. It's some distance away. If it was right at the epicenter, the P and the S waves would be together. So we actually use this differential travel time between the primary and the secondary shock waves, and we use this differential to determine how far away each one of these seismographs are from the earthquake. And so each one of these difference in arrival times is going to give us time, but it's also going to give us distance. And so we're going to take distance, and where these 3 distance circles converge, this is the epicenter of the earthquake. So the way to do that is that down here, this is a clock that represents seismographs. So all seismographs are on what's called UCT time, Universal Coordinate Time. So the reason all seismographs are on this time is you don't have to account for daylight saving time. You don't have to account for Pacific Standard Time, Mountain Time, Pacific Coast Time. If an earthquake occurs in China, you don't have to basically calculate over how many hours difference it is from China, from New York, or from wherever you're recording. So all seismographs are on the same time. So it doesn't matter if the seismograph is in Yuma, Arizona, or if it's in Bangkok, Thailand, or if it's in Russia, or if it's in England. All seismographs are on UCT time, which is actually Greenwich time, really, which is pretty close to England. And that way you don't have to convert over. So once you find out the distance, and you have 3 circles, then you use the time and convert when the earthquakes occur. So what we do here is we look at the difference of the time between the P wave and the S wave, and the P wave and the S wave for each one of these 3 seismographs. And this is done by simply coming straight down You can see the arrival time of the P wave here. So this is 1307, and each one of these is 15 seconds. So that's 1307, 15 seconds, 1507, 30 seconds, 1507, 45 seconds, 1308. So each one of these represents 15 seconds. So you come straight down and you determine where the time of arrival of the P wave, then you determine the time of arrival of the secondary wave, the S wave, and that's going to give you a differential of arrival. So I've done that. So for consideration of time here, going back up here, the difference in arrival time for the P wave and the S wave for USGS at Yuma is 40 seconds. So record these numbers on your lab manual. For the University of Nevada, Las Vegas, is 55 seconds. And San Jose, which is the seismograph that is furthest away from the epicenter, 1 minute, 55 seconds. So once we have this information, this now allows us to move forward, and we can actually now start to determine how far these seismographs are from the earthquake epicenter. The most important seismograph that we're going to use is the USGS at Yuma. And the reason for that is that the USGS at Yuma is the seismograph that's closest to the earthquake. And this is going to be really important because when we determine the actual time of the earthquake, we're going to use Yuma because it's closest. So going down, we're then going to figure out how far each seismograph is away from the epicenter of the earthquake. And the way we do that, and I've put these numbers in, so USGS at Yuma is 275 kilometers away from the earthquake. University of Nevada, Las Vegas is 350 kilometers, and San Jose is 525 kilometers. How did I get those numbers? I simply took the differential and the distances. So what I did is I took a ruler and to start at the blue line here. So this represents the S wave, the red line, and the P wave is the blue line. So as these waves travel away from the epicenter, they travel at different speeds, and this is why they depart. So at the epicenter, they're right next to each other. They're actually at the same point of origin. And so at USGS at Yuma, Arizona, I come up with 275 kilometers. So what you do is you take that time differential, you mark on your ruler, you then start at this point 0, 0, and you keep the bottom of the ruler on the blue line, and you keep it horizontal the whole time, and vertical, so just keep it right perpendicular to, use the grid lines to basically act as a, and then when your lines match up on your ruler, and this is basically where you're going to find your distance. So in this case, it goes straight down. It's basically 275 kilometers. Actually, I used the wrong mark here. So there's where my mark is. And so it goes straight down. It's 275 kilometers from the epicenter. So the seismograph, and this is how we get this. You do the same thing to the University of Nevada, Las Vegas. So I need to put another mark on. And where I get these marks is basically go back to the seismograph. So let's do the one for UNLV. So I have my P and my S. Putting my mark on this thing. Make sure I get a good mark on there. Go back to my diagram here, to my graphs. Again, starting at the point of origin, 0, 0. I'm going to hold it like this. Go all the way along here. 309 will line up with 350. Unfortunately, because of the projector, things are distorted a little bit. In fact, they're distorted a lot. So from the paper to the projector, things are distorted. So I actually did this on the graph paper. And when I did these on this particular piece of paper here, which is now blowing up, all these lined up, and that's where I got these 350 and then 525 kilometers. So now this is now distance. And so all I have to do now is take these distances and draw circles on the map. Now obviously I'm not going to be able to do that on the screen here or even on the Word document. So here are our 3 seismographs. So Yuma is the closest to the origin. So we're going to take a compass. And that's what we do is we take a compass and we draw a circle around. So let me actually get my piece of paper here. So you take a compass like this, good old compasses, and you're going to open it up using this scale here. And unfortunately, like I said, things are way distorted, so I can't even open this compass up to 275 kilometers. It opens up to about 180 kilometers. So I open up this compass, and I'm going to use this compass to draw a circle around Yuma. And then I'm going to change my diameter circle because UNLV is a bigger circle. And then same as San Jose. So how big are these circles that I'm going to draw? Well, these circles are the size of the distances. So the one I'm going to draw around Yuma is going to be 275 kilometers. The one from UNLV is going to be 350 kilometers. And San Jose is going to be 525 kilometers. So I've drawn these 3 circles on my map. I now have to turn lights on so you can see the map. Oh, come on, lights. These energy efficient buildings are crazy. So with my compass, on the real piece of paper, I drew 3 circles. So here's the Yuma circle. I start at Yuma, open up my compass at 275 kilometers and drew a circle 275 kilometers. I then did the same thing for the UNLV. There I upped it to 350 kilometers, so that's a much larger circle. And then over here at San Jose, a much larger circle. This circle actually goes off the page. We can barely see it. And where these 3 circles meet is right down here. So this is where all 3 of these circles intersect. You've had this in math where the A intersect with B intersect with C intersect. This is it. This is the epicenter. Right north, almost like at San Diego, just a little bit offshore. So this is how we determine the epicenter of an earthquake. Is we take these 3 distances, you draw on a map, and unfortunately, going from a Word document to projecting on the board, obviously the board is going to distort things quite a bit. So the circles that I actually calculated out versus the circles that I actually drew on this piece of paper here are going to be different. But this is actually the real. So once we get our 3 circles, we can then record the longitude and the latitude of where this earthquake occurred. So that's one of the next things we do. So let's move on down. So obviously I'm not going to draw on this one here. And so here, number 4, I recorded the epicenter location, longitude and latitude. And I come up with 32 degrees north latitude and 160 degrees, 30 minutes west longitude. And that's basically what we get off of these maps, longitude and latitude. So latitude goes up the page, and longitude goes across. So notice at the top it says 115, 120, 125, and then down along it says 40, 35. So 35 degrees, 40 degrees, that's latitude. So latitude goes across, longitude goes up and down. So where those 3 circles intersected, right down there, that has a latitude of 32 degrees north latitude, north because we're in the northern hemisphere, and 116 degrees, 30 minutes west longitude because we're in the western hemisphere. So that gives you the longitude and latitude of your earthquake. And now we need to find out one more thing, and that is the arrival time. When did the earthquake occur? So that's the big question is what time did it occur? And so the way we determine is during the time the earthquake occurred. So here it says that all seismographs throughout the world are in Universal Coordinate Time, UCT time, which is Greenwich England time. This system allows for standardization, and you don't have to really convert for daylight saving times because some states like Arizona do not even use daylight saving time. They don't change their clocks at all. Arizona's on Mountain Time, California's on Pacific Standard Time. So rather than worry about all of that, all seismographs are on the same time. So what we have to do in order to figure out what time the earthquake occurred is we have to now focus back on Yuma. Why? Because it's the closest seismograph to the quake. So the P wave arrived at Yuma, Arizona at 13:07:42. So in military time, that's 1300 hours, which is 1 o'clock in the afternoon. 7 minutes and 42 seconds. However, that's not what time the earthquake really occurred, because it took time for the waves to travel from the epicenter, which was right off the San Diego coast, to Yuma, Arizona. So it took time for that shock wave to travel across California, making it to the Arizona border and to the city of Yuma, something like 280 miles away. And that took about 40 seconds. So the difference between the P and the S wave is 40 seconds. And that came off that very first seismograph, the very first part of this lab. So we go up here. I can't go too fast, otherwise it'll go to pages far, far, far away in another galaxy. And this is where we get this 40 seconds right here. The difference of arrival between the primary and the secondary waves. We're not too concerned about Las Vegas or San Jose. We're really concerned with Yuma because it's closest, and this is the seismograph we focus on for the determination of the time. So we subtract that 40 seconds. And we know that the earthquake occurred at 13:07:40. So 13:07, actually it's 40, so it's actually 13:07:02. So there's a typo there that I just did. Let me change that real quick. 13:07:02. Boy, it's good to know math, huh? And 2 seconds out there. So that's the time the actual earthquake occurred. But then again, this is UCT time. which is England. Doesn't tell you about if you're living in San Diego, you have to start converting. So it says, now take the UCT time and subtract 7 or 8 hours. 7 hours for Pacific Standard Time, which is November 5th and March 11th. 8 hours for Pacific Daylight Time, March 12th and November 4th. So basically, we're going to subtract 8 hours. So take 13 minus the 8. This earthquake occurred at 5:02 a.m. in the morning. And that is basically how we figure out what time the earthquake occurred. The last thing we have to do in this lab is determine how big this earthquake was. So again, this information comes off the seismograph. This tells us what the size of the event was. Come on, cooperate with me, please. So going back up here, we take Yuma again. Why do we like Yuma so much? Because it's closest. And it also recorded the highest amplitude of a wave. So an amplitude is the height from down here. So you take the biggest wave, which is this one, and record its height. You can do it in millimeters or centimeters. It really doesn't matter. You take the amplitude. So I measured the amplitude here. And then you take that number and you cut it in half. Because you want the amplitude, not the frequency of the wave. So the total height is the frequency. We want the amplitude. So here we take the so the height of the wave was 40 millimeters. We then divide that in half, and we get 20 millimeters. And the way we determine the magnitude is we do this. We take the amplitude in millimeters, which is 20. We put a dot at 20 right here. Okay, so on this line represents amplitude in millimeters. From 0.01 all the way up to 300. Our amplitude, half our wave frequency, half the frequency of the wave was 20. So we put a dot right here at 20. And then, we are going to place a dot on the left side, and this is the distance from the epicenter to the seismograph at Yuma. So then we have to go back and say, okay, what was our distance at Yuma? And so we go all the way back here. And we know that Yuma, it was 275 kilometers. So we go back to this little graph here. We're going to put a dot at 275 kilometers right here. And then we're going to line up, and my ruler's not big enough, we're going to line up basically the 275 kilometers, the 20 millimeters of the amplitude, and when those two lines meet, it crosses right here, and this gives us the magnitude of the earthquake on the Richter scale, and that magnitude was at a 7. And I actually did that on this diagram here. I drew a line between the 275 kilometers and the 20 millimeters of amplitude, and that line intersects the center magnitude line right at 7. And this is how we determine the magnitude of the earthquake, which we recorded as a 7.0, which I have down here at the bottom. So the magnitude of this earthquake was a 7.0 on the Richter scale, and this is how this is calibrated out. And this is actually pretty accurate. And so for this, record all the information. Again, in Canvas, I'm going to go into Canvas and I'll select some questions, like I might ask you what the distance San Jose was from the epicenter, maybe the distance that Yuma was from the epicenter. What time did the earthquake occur? What was the magnitude? What was the amplitude of the waves? And those sorts of things. So all that information will come. So all the quiz questions will come off of this. So make sure you go ahead and fill in all of the information, and then use that to go into Canvas. This is kind of a strange lab to do, again, by a Zoom lecture. It's so much better when we're running around the room, when we're actually drawing our circles. Not everybody's circles come out to be pretty precise. I mean, some people hold the compasses differently than other people. So take all the information, record it, and then use that information to answer the questions in Canvas. And that basically ends this lab.